you're going to need to have your Chapter 3 notes packet out, along with making sure you have a pair of headphones in, and then make sure that you have something to write with. We're going to go through the notes for 3.6 today. When you're finished with the notes, then you're going to work on the assignment that is for this lesson. All right, so we're going to start just by going through different types of triangles. You can identify triangles by their sides or by their angles. So we're going to start by going through the types of triangles based upon their sides, okay? So their sides, we can identify triangles as either scalene, isosceles, or equilateral. Pretty confident that you're familiar with these different types of triangles, but let's just briefly go through them. So a scalene triangle is where no two sides are congruent. So all the sides will be different lengths. Isosceles triangles are a triangle in which at least two sides are congruent. In an isosceles triangle, we have two sides that are congruent. Those are called the legs. We're going to be talking a lot about that in this chapter and then triangles going forward. The angle that makes up the two legs, so if I know these two legs are congruent, the angle that is between those two legs is called the vertex angle. So the vertex angle is right there. The angles that are made that are across from the legs, so the ones that are directly across from the legs, are called base angles. So this is some pretty important vocabulary to know because we're going to be talking about that very regularly throughout the rest of the time we're talking about triangles. So an equilateral triangle sounds exactly like what it is, since equal means equal. It's a triangle in which all sides are congruent. So we can represent that by having tick marks here as well. All right, so then we can also name triangles by their angles as well. So let's start with an equiangular triangle. Similar to equilateral, equiangular, since you have the prefix equa there, it's equal angles. So it's a triangle in which all angles are congruent. Then we have a triangle called acute, and you're probably familiar with an acute triangle. So an acute triangle is a triangle in which all angles are acute. Okay, so all three angles are acute. Okay, a right triangle is exactly what it sounds like. A right triangle is a triangle in which one of the angles is a right angle. The side opposite the right angle, you probably remember this from algebra, hopefully, is called the hypotenuse. So you have a right angle, it makes it, if you have one right angle, it makes it a right triangle. And the side that's across from that is called the hypotenuse. Because the right angle is the largest angle in a right triangle, the hypotenuse is also the longest side of a right triangle. And then we have an obtuse triangle, a triangle in which one of the angles is an obtuse angle. Okay, so you have one angle like this that might be 100 degrees. So why can't there be more than one obtuse angle? Well, you should know that all triangles have a sum of the angles that is equal to 180 degrees. So all triangles have a sum of 180 degrees of their angles. Okay, so any triangle that I add all the angles, they're going to have 180 degrees when I add them together. Now, if I have one angle that's obtuse, there's no way, even if you take the smallest obtuse angle, which is 91 degrees, okay, that I can have a second obtuse angle. So if I had a triangle and I had a 91 degree angle, I still have another angle that would have to be obtuse, which is 91. So far, if I add those together, that's going to give me 182, and that's already over the sum of 180. So there's no way that we can have more than one obtuse angle. And the same thing is true for right angles. There's no way that you can have two right angles in a triangle, because two right angles would be 90 and 90. So I'll just give you a little drawing here. Okay, so if I have 190, and if I had another one that was 90, it's already trending in a direction to not look like a triangle, but mathematically, 90 and 90 is 180, which does not leave me any measurement for the third angle. All right, so we're going to move on to packet page 16. We're going to do some proofs here. So let's go ahead and get our statements and reasons. So I know angle CBD is 70 degrees. And I'm trying to prove ABC is an obtuse triangle. Okay, well, you probably know that we have ABD is a straight angle, which we don't have to actually state in our proof anymore. But we can say angle ABC is 110 degrees. We know this angle is 110 degrees because we have to do 180 minus 70, which is 110 degrees. Okay, and we just did some subtraction there. Now, before we can just go ahead and go to the subtraction, if you look at the flow of your proof, you're going to notice that I need to have stated in the proof that it's 180 degrees. So I'm going to go ahead and add a step here. I'll call it 1A. Even though I don't have to say it's a straight angle, I do have to say angle ABD is equal to 180 degrees. And my reason behind this can just be, I'm going to kind of write this up here. If an angle is a straight angle, then it is 180 degrees. So now I can show how the subtraction actually occurred. So again, I don't have to state that it's a straight angle in my proof, but I do need to state that it's 180 degrees because that's how I actually do the subtraction. Now, the definition of an obtuse triangle is a triangle that has one obtuse angle. So I know 110 degrees is an obtuse angle. So my next step is going to be angle ABC is an obtuse angle. So if an angle is greater than 90 degrees and less than 180 degrees, then it is obtuse. So since I have an obtuse angle, I can go ahead and say that triangle ABC is obtuse. And I can say if a triangle has one obtuse angle, then it is an obtuse triangle. Feel free at any time through the video to go ahead and stop and pause. If you need to re-listen to something, you can rewind. Or if you just need a pause break because you need to be able to write, you can do that as well. All right, we're going to go ahead and go on to packet page 16. We have a proof here, so let's go ahead and do that proof. Okay, so the first one says EG is equal to FH. So EG is equal to this whole side here of FH. And I know that side EF is greater than side EG. So EF, it's a different length, but EF is greater than EG. So we're trying to prove that this triangle is scalene. So in order to prove that the triangle is scalene, I need to go ahead and have 3 different sides to start. So in order to prove that I have 3 different sides, the first thing I'm going to do is try to think about how could I potentially get that side FG in the triangle? How can I potentially show that that side is going to be a different length than the other 2 sides? And we do know that we have 2 sides in there that are congruent. So we know EG is congruent to FH. So I know mathematically that FG has to be a shorter length than EG. So now how does that look in a proof situation like this? So that's what we've got to talk about here. So mathematically I know that it works out, but how am I going to show that in a proof situation? We've never actually had a proof that we've gone through that have had things like greater than, equal to in it like this. So this is slightly different than anything that you've had to do up to this point. So first step is to make sure that you understand mathematically how that works. Once you can understand that mathematically that works, how can we go through and we can actually represent that in the proof? So the next thing that we're going to do in order to get that is indicate that that side ends up being smaller. But this is kind of hard to actually state in a 2-column proof situation. So we're going to go ahead and just write, instead of a 2-column proof, we're going to just go ahead and pretty much just give a little description of that. So it's more of like a paragraph type of proof. So I'm not going to indicate with a 2-column proof, but I'm going to do a paragraph proof. Okay, so I could say something along the lines of, since EG is equal to FH, FG must be shorter than FH. FG will also be a different length than EF, since EF is larger than EG. So if I put some numbers to this, like let's just say that this is 10 and this is 10. This side EF, it tells us right here, is, oops, block that off a little bit. EF is bigger than EG, so this one already has to be larger, so this has to be something like 12. So no matter what size GH is here, let's even just call it 1 unit long, this is going to be 9, it's going to be a different length. Okay, so let's see if this makes sense. Let's reread our paragraph proof here so far. So since EG is congruent to or equal to FH, FG must be shorter than FH. FG will also be a different length than EF, since EF is larger than EG. So then we're going to use our little 3 dots there. So therefore, the triangle must be scalene. All right, so we're not going to do a ton of paragraph type proofs like this, but a 2-column proof would be really hard to try to represent that in there in an if-then statement. It's more of like a logical proof. So if you notice that something like that pops up, just know that having something like a 2-column proof is an option. All right, we're going to go ahead and go through our last proof. This one is a 2-column proof. So we're going to go ahead and state angle 1 is congruent to angle 3. Mark your diagram. I'm going to state angle 2 is congruent to angle 4, also given. I'm going to show that JP is congruent to PO. Additional given. And I'm trying to prove triangle KPM is isosceles. Okay, so in order to prove a triangle is isosceles, I need to get its two sides congruent. Okay, oops. So to prove isosceles, we must get KP congruent to PM. So hopefully we can get that done by proving a set of triangles congruent. Now we did work through last week trying to identify which triangles we would actually need to be congruent in order to solve a proof like this. Okay, so if I look at this, I've got a lot of different triangles here. I'm going to highlight them. I'm going to start by highlighting two orange ones, so I could try to get these two orange ones congruent. Or hopefully you see the larger green. Okay, now again, I would try to logically reason through how can I use the information that's been given to me in order to prove what's congruent. So I look at it, and I'm going to just start with those orange triangles. So let's go ahead and let me get rid of the green there. All I can prove in these orange triangles, and I'm not writing in my proof yet, but I'm just talking you through it. I could prove that these vertical angles are congruent. And I'm just going to ask myself the question, do I have enough information to get angle J congruent to angle O? Because if I could get these congruent, I could have those triangles are congruent by ASA. And I don't have anything that gives me any indication that J is congruent to O, so I'm not going to be able to use that. And then I'm going to look to see, well, could I get these triangles congruent by side angle side? So I'm going to talk about, could I get those sides congruent? Well, in reality, that's what I'm trying to get congruent. That's right here, what I'm trying to get congruent to prove that those triangles are isosceles. So I'm not going to be able to use that either. So what I'm going to go ahead and end up doing here is trying to see if now I can get the larger triangles. Like, do I have enough information to get these green triangles congruent? Well, they already share an overlapping side. They share this side here, okay? And remember, if it helps you to draw them separately, go ahead and do that because you might visually see what's going on. Because those are actual overlapping, unlike the orange ones we were talking about. So like these sides would be congruent. I also have this angle here would be congruent to this angle here. And if I add angle 1 and 2 together, and I add 3 and 4 together, I'm going to have another set of congruent angles that are here in the corner. So I could get these triangles congruent by angle side angles. So I think that's what I'm going to go ahead and do. So let's go ahead and let's say angle JKM is congruent to angle OMK, and that's because of addition. So I can say triangle JKM is congruent to triangle OMK because of angle side angle. And I needed step 4. I didn't need step 3 yet, and step 2. So now you might be wondering, why did they give me this JP congruent to PO? Because that's part of the side here, like in this triangle. Like this would be JP and OP, those are congruent. Well, I know that the entire side, like JM is congruent to OK. I'm going to put that in my proof because I'm going to need it. Those are congruent because of CPCTC. So how I can say then that KP is congruent to PM is through subtraction property. So once I subtract, I can get those two sides are congruent, and that's enough to prove that the triangle is isosceles. I'm going to use my definition of isosceles to turn this into an if-then statement. So, if a triangle has at least two congruent sides, then it is isosceles. All right, so your assignment is going to be to go ahead and do day 7. You're going to finish slides 7 and 8. And when I return tomorrow, I will go ahead and go through this assignment and the assignment from Friday. If you have any questions or anything, feel free to shoot me an email and I will try to get back to you, or we'll just talk in class tomorrow. Have a great day and I'll see you soon.